the chain rule, what happens when you have one function inside of another function? So there's two notations. The notation which everybody likes, underlined here in green, f of g of x, because it's really easy to see that g of x is inside of f of x. And then there's the notation which I'll underline in blue here, which means the same thing, but people don't like it as much because it's not as clear. F composition of g, I call it the foggy notation because it isn't as clear. Okay. Find the derivative of this. Now this is a composition of functions because we could see that the line 3x plus 2 is getting cubed. So we would say that the function 3x plus 2 is inside of another function cubing. If I wrote it like this in function notation, if I made g of x equal to 3x plus 2 and f of x equal to x cubed, can you see that f of g of x is equal to f of, instead of g of x, I could write 3x plus 2. And what does the function f do? It takes whatever you put inside and cube it, so this would equal 3x plus 2 cubed. So that's a little review of function notation and composition of functions. Now, right now, if you wanted to find the derivative of 3x plus 2 cubed, the only method we have is, well, we have two methods. Okay? The best method, I'm going to say, that we have is you take your 3x plus 2 cubed and you expand it. Expanding, method 1. Multiply two of them. Everybody okay with multiplying? Was that I did that fast, right? I multiplied 3x, right? This times this, that would give me 9x squared. This would give me 6x, this would give me 6x. That's how I got the 12x. And then 2 times 2 would give me the 4. That's still multiplied by another 3x plus 2. And then we would multiply that out, which would give me 27x cubed. I'm going to get 18x squared plus 36x squared, 54x squared. I'm going to get 24x plus 12x plus 36x, and 4 times 2 plus 8. Whew. And again, if you want to, when you're doing this, if you're multiplying out, right, all of these, this 3x is getting multiplied by each of those, the 2 is getting multiplied by each of those. I've multiplied these lots and then added like terms, so I did it really quick. But are you okay with just having the answer there? Hoping I didn't make a mental math mistake along the way. Okay? So we could have expanded it this way, just because it's fun to review. We could have expanded this with Pascal's triangle and the binomial theorem. You know that there's going to be 1, 2, 3, 4 terms in the end. So in Pascal's triangle, that would be that row of Pascal's triangle. And the expansion would be 1, and then the first term to the power of 3, plus 3, and then their first term to the power 2, and our second term once, plus 3, first term once, second term squared, plus 1, second term cubed. If I multiply this out, 3 cubed would be 27x cubed. 9 times 6 plus 54x squared. 4 times 9 plus 36x plus 8. Did I get the same answer? Yes. Oh, That's exciting. So I could use what I learned about the binomial theorem from grade 12 to expand this as well. Now, if I expanded this, my derivative becomes really easy. I just bring the 3 out in front, 81, subtract 1 from the exponents, 2 out in front, 108x, plus 36. It said write your answer in factored form. So writing my answer in factored form, well, what do I have in common between 81, 36, and 108? I can factor out a 9, leaving me with 9x squared plus 12x plus 4. 9. This factors nicely to 3x plus 2 times 3x plus 2. So I'll write that as 3x plus 2 squared. View the entire page that we've done so far. There's got to be a shortcut that I can just look at this and get my answer right away. My answer, after doing it in factored form, was 9 bracket 3x plus 2 bracket squared. And notice, if I go back to the beginning, so we just figured out that our derivative was 9 times 3x plus 2 squared. Notice you would be very tempted to use your power rule. If I used my power rule, just my power rule, the 3 would come out in front, subtract 1 from the right. This took us what? 3 seconds to write? And it's just a little bit off? So we should be, it's close enough, right? For saving all that time. Unfortunately, mathematicians don't like to be close enough. They like to be right. So we got to figure out, oh, why is this difference here? What happened? If we can figure out what happened, maybe we can make a shortcut. So the next thing you do to find a shortcut is you do this process that we just did over a bunch of times, even with really, really big numbers. Luckily, I've done it for you. And you look at your answers when it's in factored form. And now, in factored form, you would have not gotten it like this. This first one, you would have probably written this. Just like we had a 9 out in front, you would have put the 2 and the 5 together and written 10. Now, I've kept the 2 and the 5 separate to help us see something. Because in the first one, if we go back to the one we just did, there's an extra. The actual answer is exactly the same, right? But there's an extra 3 to make it work. And so looking at the pattern, this first one looks like the power rule works, but there's an extra 2. And the second one looks like the power rule works, but there was an extra 6x. The third one looks like the power rule works, but there's an extra 4 cubed minus 1. And the last one looks like the power rule works, but there's an extra 5x to the 4. So when we're looking at this, right, the underlined yellow part is just your regular power rule. But we have to figure out, why is there this extra part here? And if we can figure that out, we can probably explain a rule, and that rule is going to be something called the chain rule. Ideas? Yes? Well, you know already, so that's not even fair. Yeah, we've just got the derivative of whatever was in the inside. So this one, oh, it's got two things, but that's just 4x cubed minus 1. It's the derivative of the inside. So this is called the chain rule. And notation for the chain rule is a little bit, sometimes a little bit not nice. And I've got it in two different forms there. If y is a function of u, in either way, I shouldn't use u here, because when I read this, y equals fu. And u is a function of x. This is better, u equals g of x. In other words, we have one function inside of another function. Then the derivative is, okay, I'm going to explain this. This is the words I'm going to use lots of times when we talk about the chain rule. We're going to call this the derivative of the outside function. Bracket, I'm always going to say keep the inside function the same, multiplied by, this is the derivative of the inside function. If we were color coding things compared to what we had before, this is what I had underlined in yellow. That was your just normal power rule multiplied, and this is what I had highlighted in green, derivative of the inside function. The notation is kind of weird, though, when we're looking at this. So sometimes I find, especially in calculus and higher level math, when you look at the notation the first time, your brain capacity is not at a level where you can fully comprehend it yet. And be okay with that. Be okay with notation not making sense to you at the beginning. Then you're going to practice the chain rule and get a sense of it and do it enough times. And then afterwards, you're going to look at the notation again and say, now that have experienced the chain rule and done it enough times, does this notation make sense to me? So I'm not going to try to make the notation make sense right now. We're going to be okay with that. I think the next notation is going to be easier to see. So if we look at easier to see, I'm going to, whoa, no, that's not what I want to do. I'm going to copy what I had done here. It's the same thing in a different notation. Oh, here, this will work. There we go. That arrow should match up with it. That's the derivative of the inside function. Oh. Perfect. Close enough. Arrowhead looks nice. Excellent. I think in this notation, you can see the derivative, f as being the outside function. We do the derivative of f, and we keep the inside the same. This notation, I think, really highlights that the inside stays the same, multiplied by the derivative of the inside function. So of these two notations, I prefer this one as far as being able to understand it. I find the Leibniz notation is a little bit harder for students to see right away and understand. But either one, what we're looking at when I go back to what we saw originally, Our outside function is to the power of 5. Our inside function is the 2x plus 3. So if you did the derivative of the outside function, how do you do a power rule with the power of 5? You bring the 5 out in front, you subtract 1 from the exponent, and you keep the inside the same. Number one mistake with chain rule is over-deriving. You try to do too much at once. Derivatives, they want to keep things simple. You just do one simple step at a time. We do the derivative of the outside function. 5 comes out in front, subtract 1 from the exponent. Then we multiply by the derivative of the inside function. What's the derivative of 2x plus 3? It's 2. Outside functions to the power 40. That 40 comes out in front, subtract 1 from the exponent, kept the inside function the same. Then multiplied by the derivative of the inside function. Even though you have the binomial theorem, you could expand this. You would have 41 terms. And then, if you wanted to, you could use your factor theorem and remainder theorem and synthetic division and factor it 40 times, 39 times, to get this expression times by 6x. That would only take a couple of days. It's not so bad. But this, taking a couple of seconds, is a lot better. So we notice this idea that we keep things simple, just the outside, and then keep the inside the same, multiply by the derivative of the inside. Okay? So one of the things that calculus is going to do for your brain, I would say the chain rule, which if we describe it as derivative of the outside function, keep the inside the same, multiplied by the derivative of the inside function, is a rather simple rule. We can say it in under 10 seconds. Okay? But can you deal with simple rules when you have complex situations? When you're dealing with complex-looking functions, can you keep your data straight, what's inside, what's outside, and do the derivative as you go? Because what we do now is, now that we've got our basic rules, now we add layers of complexity. What happens when we put a chain rule together with a product rule? A chain rule with a quotient rule. A chain rule, product rule, and quotient rule. Double product rules. Double quotient rules. Can you maintain the data and keep the rules simple even though the situation gets complicated? So let's look at a couple of examples. Oh, yeah, and let's look at, okay, I'm going to show you the Leibniz notation, and you're never going to use it again for a long time because it's just so painful to use. But we'll walk through Leibniz notation and how you would go about it. Okay? So this is where we want to find dy dx using this first chain rule formula. Okay, so if you forget, or if you are in need of a mental break and you're not going to pay attention sometime during today's lesson, I shouldn't ever say that, but this would be the time that you would, okay, just need to refocus and take that break, because I don't like this notation. So if you didn't learn this and you don't know it well, I'll be okay with that. Leibniz is probably rolling over in his grave and cursing my family, but it's okay. So what happens here is we notice the outside function is to the power of 5. So instead we make a substitution. We say that the inside function u is equal to 3x plus 6. And then I could rewrite my equation as y equals u to the 5. Okay? If I have that, then what's dy du? I have y is equal to u to the 5. dy du would be 5u to the 4. dy du is the same as dy dx. It's just you have different variables. Instead of an x, you have a u. It shouldn't be that crazy. And later on, when we do them the regular way, you'd be like, why would I spend all this extra time doing this? Yes, we're not going to do this often, but dy du would be 5u to the 4. Du dx, well, I've got my equation. Instead of dy dx, which we normally find, now we've got u equals instead of y equals, so it doesn't make it that hard. What's the derivative of 3x plus 6? 3. So using our formula, we can now say that dy dx is equal to dy du, 5u to the 4, multiplied by du dx, which is 3. And if you undo the substitution that you started with, then dy dx is 5. U was 3x plus 6 to the power 4 times by 3, which you could multiply the 3 and the 5 together and make 15 if that makes you really happy. Or you could leave it like this if it doesn't ask you to simplify. What are we going to do instead? We're going to just do it directly. If you have y equals 3x plus 6 to the 5, you're going to say dy dx is, recognize that my outside function is the power of 5. Bring the 5 out in front. Keep the inside the same. And then multiply by the derivative of the inside. Does this not seem much more reasonable and a lot less writing to do? If we can manage the data and see what's our outside function and what's our inside function, we'll be able to just write this right away. Okay? Now, later on, okay, this isn't all for naught. If you didn't pay attention, that's fine. If you did pay attention and say, Mr. JR, if you were teaching us something that we weren't really going to use, what was the point? Well, later on, this notation does come in helpful when we're working backwards. When we get into integration and we have to undo things that we did, this will be helpful. But until then, which is still 2 units away, don't worry about this. But you've been introduced to it. From now on, okay, we're going to get things so that we can see inside functions and outside functions. Often, you'll use some of your algebra skills to manipulate first. So in this situation, I have x squared plus x as an inside function inside a power of 4. That's going to be a chain rule. When you have one function that you can do the derivative of inside of another function, you're going to have the chain rule. Right now, we have a quotient. So I could use quotient rule, but then I'd have quotient rule and chain rule. Or we can do some manipulations to make this easier first. I'll show you both ways. I'll show you what I think is the easiest way first. Easier, I would say, manipulate the equation first using your exponent laws to write your power of 4 as a power of negative 4. Does that make sense? And now my outside function is the negative 4. The x squared plus x is the inside. So if I do the derivative of the outside, the negative 4 comes out in front. Keep the inside the same. Subtract 1 from your exponent. Multiplied by, what's the derivative of my inside function? 2x plus 1. If you didn't have to simplify, you're done. Nice. Okay. Let's say you didn't see that you should manipulate it first to get your regular power rule. If we can get things with the power rule, it's like the easiest derivative rule, makes our life easier. But sometimes your brain doesn't work that way. Sometimes your brain sees something first, and we have a quotient, and we have a quotient rule. It is very likely that your brain will see that first. Can you see that if you have a quotient and a quotient rule, you would see that pretty early? Right? No, you wouldn't. I have no idea what to do. But if you thought, I want to use the quotient rule, well, what's our quotient rule? Our quotient rule says, keep the bottom the same, x squared plus x to the 4, multiply by the derivative of the top. What's the derivative of 3? 0. Minus, keep the top the same, multiply by the derivative of the bottom, and the derivative of the bottom is a chain rule, so you would have to bring the 4 out, keep the inside the same, subtract 1 from the exponent, multiplied by the derivative 2x plus 1 of the inside. Sorry, it's a little bit small. I'm going to make this smaller, move this over, and make this bigger. Multiplied by the derivative of the inside all over the bottom squared. That's your quotient rule. Do these two answers look the same? Well, not yet. Okay, if I simplified this one, I would have negative 12 2x plus 1 over x squared plus x to the positive 5 if I move that exponent down. In this equation, this will be 0. Negative 3 times 4 is negative 12 x squared plus x cubed times by 2x plus 1 over x squared plus x to the 8. And perhaps you can see that these factors are the same. So if you simplified them, you'd get negative 12 2x plus 1 over x squared plus x to the 5, and those answers are identical, which is good. There shouldn't be derivative rules that give you different answers if you decide to use different ones. So we could use the quotient rule, and either way, your algebra simplification will give you the same answer. So again, the key thing is when you're working on questions in your homework, I want you to look at the answers. I want you to look at the answer key, and then with whatever method you chose, can you manipulate your answer to match the answer key? Not just copy down the answer key. Yeah, it's the same. But actually algebraically manipulate it to make it match. Because that, you're going to find, is probably one of the greatest skills that you're going to get from this course, is just enhancing your algebra skills to make things match. All right.